Hopefully the orientation doesn't mess up. Anyways, good evening, Dr. Elaine. The following problem is number 38 on page 167, and it's dealing with Young's modulus. In this problem, we're given the mass of the ball, the length of the wire, how the wire is stretched, and the diameter of the wire. Basically, what the question is asking is the Young's modulus of the wire and the interatomic spring stiffness for gold for each atom. So, to find the Young's modulus, we use the equation y equals stress over strain, where stress is equal to the force over area, and strain is equal to delta L over L, where delta L represents the compression or stretched, and L represents the initial length of the wire. So, the force on the actual system, the object, since the mass is suspended from a spring, we assume that gravity is pulling down on it. So the force on it is just m times g, which is that right there, 14 times 9.8. The area is pi r squared. We were given the diameter on the original, so radius is same as the diameter cut in half. So we have to convert this. That was a very crucial mistake I made in the first attempt. You have to convert 0.2 millimeters into meters, because millimeters is not a SI unit, and so an area that has to be meters. So we get 3.14 times 10 to the negative 6 meters squared. Finally, it's just plug and chug. We'll plug and solve. So once again, Young's modulus, stress over strain. We have all the calculations. So the biggest thing was to check for units over here. This side right here, meters over meters cancels, and we're left with newtons over meters squared. Newton is kilograms per meter per second squared, so you really have kilograms over second squared times meters, if I'm not mistaken. Next, we have to find the interatomic spring stiffness for each gold atom. So first, I used the Hooke's law, which is F equals Ks times X, where F represents force, Ks represents the spring stiffness, and X is the length of the compressed or stretched spring. We said F equals that, and in the original Young's modulus it said y equals force over area. So we can substitute force for K times delta L. It should still be the same thing. And when we simplify, we just get Ks equals y over Al, which is YL. So to solve for Ks, we multiply the Young's modulus for the wire times the original length of the wire, and we get 2 times 10 to 11 newtons per meters. Once again, the units here for spring stiffness is newtons over meters. The meters cancel in the numerator and denominator, and you left with 1 meter on the bottom. So this is the spring stiffness. We have to find the interatomic spring for each atom. So from chemistry, we know that there is, it gave us kilograms, so I switched it to grams. So we know that in 14,000 grams of gold, which is in one mole, there is 197 grams. So you convert that into moles. So there's 71.06559 moles of gold, and of moles in gold of 1,400 grams. Okay, that was a mouthful. So you convert that into atoms, which is, to find atoms is the number of moles times Avogadro's number. So you have 4.28010 times 10 to the 25. Lastly, to find the string stiffness, you're multiplying the 2.10 times 10 to the 11 meters, which we found in the previous section, which was the spring stiffness, divided by each atom. Since each atom acts like a spring, once the object is pulling on it, each atom will act like a spring. So therefore, the string stiffness is 1.660 times 10^24. Once again, the units is newtons per meter, because atoms will now play a role in canceling anything out. So thank you.